Hello and welcome to this week's episode of Programming Quantum Computing. We've got our usual suspects here, and this is our last week of a 13 plus week journey. And so really want to thank everybody who's been with us either in person or virtually, and hopefully you've got a lot out of this journey and you'll continue learning. So I'm going to get right into it because this chapter is mind crushing, right?
Yeah, compared to last week where I kind of got the gist of what was going on, chapter 13, I got lost pretty quickly.
Yeah, so I'm going to go ahead and share my screen. And the approach I'm going to take is I am going to kind of go in and out of the book because this is a really difficult topic, and the authors took the approach that they took in the previous chapter, which was Shor's algorithm, which is the typical how you actually work with this. There's a quantum part and there's a classical part, and they wanted to focus on just kind of one quantum operation that is used in a lot of different machine learning. But I found that thinking to be really challenging, and I have done machine learning, and I can't imagine if you haven't done machine learning how that would be. There's just too much assumed knowledge. So where we're going to start is start with a chapter. QML is the greatest combination of buzzwords. Yep, might as well say QML blockchain, right? Or crypto. So it's overhyped and undersold. Going to give, and they say you're just going to give flavor for how it might affect machine learning, and then with some reality checks, some caveats, and they start off with something that's really, really important. Useful QML applications require a really large number of qubits, and then they say because of this, our overview is very high level, and also the field is really rapidly changing. It's like a real rapid area of research. So the approaches that they choose to include, I kind of quibble with them. And so we're going to actually take a little side tour and then come back, because I see it as a very piecemeal part of the space. And also when I go and I look at examples out on vendor cloud machine learning implementations, they don't align with what's presented here. So this is, to me, kind of overly academic. So that being said, we're going to just jump off and we're going to do something which I hope you guys will think is a little bit fun, because I know that both of you do not have a background in machine learning, and maybe some of the people watching don't as well. And I have taught machine learning and I've practiced machine learning. I'm still, I would say, kind of an advanced beginner, but I've done a little bit. I'm just going to kind of take you through this visual tour to kind of shore up some of the gaps, I think, in this chapter. So starting with, if you've never done any machine learning at all, this is what's taught at the universities, and it really helps us to really kind of get like a baseline. It's a Python library called scikit-learn. And it has lots and lots of examples. And importantly for our discussion, it starts with 3 pictures, because what I'm going to do is take you through a rapid series of basically pictures to explain some of the concepts that the book either skips or assumes that you have knowledge, which I think is important to understand what they're presenting. So the first thing is, in machine learning, there's basically 6 types, but the top 3 here are the sort of key areas that machine learning has solutions or algorithms for, and they're classification, regression, and clustering. Classification and regression are called supervised because they require data that is known good or known correct, and clustering is unsupervised because you can just take the algorithm and throw it at any data and we'll find the clumps or clusters. Importantly, from these 3 pictures, classification is finding out, in the picture here, it's red or blue. Is your data part of the red or blue data set, which might look like, well, why would you need an algorithm for that? Because I can just look at it. But they're simplifying the dimensionality of it here. The idea is, how likely is this data part of a category? That's classification. Regression is given a certain X, what is the likelihood of the Y? And that can be a line, or as it shows there, it can be a point in space, which can be 2D, 3D, or ND. Clustering is given the data I have, how does the data tend to group together? So at a very, very high level, you think of problems in ML as classification, regression, or clustering. Now, there are some other types, but those are kind of the main ones. So how does that relate to a QML? Well, again, and I put a text file up on, well, here, I'll just show you. I put all these links up here of all these pictures. So if they're helpful to you, you can just see these pictures. Plus, I didn't make any of them, so picture credit. So this basically takes the same idea from scikit-learn and it applies it to quantum, and it links to papers. So for example, if you are interested in clustering and how quantum methodologies can impact that, you would look in this section right here. And these are some of the key types of algorithms that are available out there. So the one that I find as a practicing machine learning technologist that is getting the most play around optimization, so that's what quantum does, it optimizes, is neural networks. And neural networks is a classifier that you train with known good data, and then you can use it to predict what class new data is of the likelihood of being a part of. And the simplest possible explanation I saw of this is this single explanation here that shows that you have input, then you have one or more hidden layers, and the or more is important to our discussion, and then you have an output layer. And the W and B are weights and biases, and those are what are determined by the implementation of the algorithm. So this is sort of like the baseline for a neural network, if you've never seen one before. And of course, we work in n-dimensional space. And so the configuration of your neural network is going to depend on what your input data and what kind of problem you're working with. And as you can see, as you get into more and more types of problems, your network becomes multi-layered. And this is represented, I think, pretty well by this diagram here. Just to give you kind of like from the real world, it's not uncommon to have 5 to 12 layers in some of the neural networks that some of my customers have worked with. So the single layer is not something you really see much in the wild out there. In fact, I love this. This is from Reddit, or it was posted on Reddit. Whoever made it is listed on it. There are different architectures for neural networks depending on the types of problems that you want to solve. And why this is relevant to a discussion of QML is because QML is used to optimize one or more of the layers, but it depends on the architecture of the neural network because of the limitations of quantum operations. So in other words, you can't just say, okay, I want to optimize all the pink dots in the middle there with QML. It doesn't work that way. It's not just like throw a QPU at it and it's going to be faster. You have to understand the way the problem is being solved. So again, that's why this is so mind-bendingly complicated, because you do have to understand the math to understand if it's possible to even try a QPU speed up. In fact, this is kind of interesting. There is a gal, and she got hired by IBM. For her grad work, she went to prove for a certain problem space that QPU speed up would be important when enough qubits were available. And what she actually proved is that it wouldn't work. And so she got the opposite result, and her research led to some advances in the classical implementation of this architecture of a neural network that was really significant. So it's like really ironic result. She was out to prove, quantum superiority, and she proved classical superiority for this one case for the current state of quantum. So it's when the book authors say it's a really active area of research, they mean it. So the problem that is used, there are two demo problems that are used to set up neural networks, to test neural networks, because again, to our point of quantum neural networks, you would want to set up your neural network for your particular case, and then you would want to determine if a quantum speed up was possible, and then you want to test and see if your idea around how this is going to be processed would actually result in a quantum speed up. So there are really two types of problems that are used to test neural networks, kind of like benchmark them. And one is MNIST, which is a set of handwritten digits, 0 to 9. And then you create in this case, 1, 2, 3, 4 layers of neurons of different size to analyze the pixels. And this is, again, just background information. But again, the thing that the book is actually presenting, the operation around optimization, this is where you would apply it more so than what they show in the book, which is a simpler algorithm. I'm going to just pause here because I've been saying a lot of words. Does anybody want to add anything, or is this making sense?
So is this a classification problem, right? If
Yes.
you're doing image,
Yeah.
okay.
Yeah. Okay, all right, so we're still on the classical side, basically. So again, just to give you a path, if you're wanting to learn about this, one of the most powerful libraries for neural networks is Google created, but it's open source, TensorFlow. And they have a series of tools to help with visualization because it's so complicated to do the math, basically. And this is a screenshot from TensorBoard, which is a tool that really every customer that I have that uses TensorFlow uses this because when they're developing, because it visualizes. In this case, this is a classifier and it's 2 colors, and you can literally see how each of the layers is interpreting the values so that you can make adjustments to the parameters or the number of neurons in the network, because you can see the flow basically through it. And in terms of usable tools to see into the black box, if you will, I think that I haven't really seen anything as sophisticated and useful as TensorBoard. So it's something that I would definitely use if I were using TensorFlow. And I think that it actually works with some other neural network libraries as well. It's just the best thing out there, because again, the problem space is to determine whether and how a QPU optimization would impact the execution, in this case, of a neural network. So here's just another example. Again, I like the visual intuition around this. I don't know, hopefully you guys are finding this helpful. So another sort of quintessential problem is in a photograph, what is the object in the photograph? In this particular model is it a car, a person, or an animal? But the really quintessential one is it a cat or a dog? So that's Jeff Dean, who's the machine learning lead at Google. He jokes that they have spent, $27 billion to analyze YouTube videos with neural networks to find out that the most common image is a cat, which maybe is a different kind of sad commentary on our society, but it's a fact. Anyway, so you can see in here.
That's probably a wealth of free data that they've got that they can mine. We can visually see. And this is interesting for me only because at a school district, we have security cameras and everything everywhere, but only in the last couple of years has it been affordable for a K-12 school district to actually get real-time analytics. And it's not just whether there's a car or a person, but it's literally, there was an incident and we were told that the 2 of the people involved, one had a red shirt and blue jeans and the other one was a girl wearing a black top. And we can literally go through and and it'll find it for us across all our cameras. We could look through it and timeline and everything. And that's something that used to take hours and hours and hours. And now we can find it in seconds. And this was not affordable even 3 years ago. So this is exciting to see this coming. And I'm excited to see where quantum's going to take place.
Well, the reason I take the time to show this is because it's a whole separate talk that I do, but I not only am excited about that, but I believe that we as educators and learners have an obligation to educate, because where the state of the public is and the neural networks are black boxes and you can't see into them. And what that's resulted in is a lot of societal problems around bias. That is just a really fascinating area. So again, with these visualizers and these tools that I'm talking about for performance, they have a side benefit of they provide some visibility into the workings of the algorithm. So they're doubly good. So anyway, so this is, a pictorial representation, and the library that's being used here, kind of an aside, since you guys are in California, at UCI and at Irvine, there is a tool called LIME, and I forget what the acronym stands for, but what it does is it produces these pictures. And it shows at each of the layers what parts of the image is being used by the neural network. It comes out of graduate work of the CS machine learning department. And it was when I lived there. So it was a few years ago, I went to a presentation, and it was very interesting because it was, is it a dog or is it a wolf? And what it was actually doing is it was classifying the background and not the animal. So is it a snow classifier or a grass classifier? It was so fascinating. In any case, this LIME library has been incorporated into TensorFlow. So that's where this is coming from. So Google really has shown that they have a lot of tools. Now, to be fair, I haven't looked in depth at IBM yet, but I will because of their quantum implementations. But from a machine learning standpoint, the ability to see into whichever algorithm, and I happen to be going with the most difficult one here, so sorry, but that's the one you'd want to optimize, right? Is an important part of using quantum for machine learning or not. So, right? All this aside, the book authors say, well, we can just, use quantum and we can figure out if it's a cat or not. Well, it doesn't go that way. The way that you really want to think about it is kind of as we did in chapter 12 with Shor's algorithm. There'll be a classical part to the machine learning problem. So classical machine learning, if you will, or non-quantum. And then there'll be a quantum part. And particularly in machine learning problems, we already have specialty hardware. TensorFlow was built to take advantage of GPUs and the Google version, which is a TPU or a tensor processing unit, to offload some of the linear computations. And of course, for other types of problems, there's FPGAs and other types of specialty hardware. So for those of us working in machine learning, the ability to swap out a GPU or a TPU for a QPU is really, really makes us salivate. Like, is this really gonna, 10,000x our problem or not, right? So it's more common in the machine learning space. And in fact, in the cloud vendors implementations, you already start to see, do you want to use TPU? Do you want to use QPU? It's already coming. This is a slide from Amazon. You can tell here. So I just love this picture. I always like to have visualizations. So when I think of my quantum neural network, there are my beautiful qubits spinning. And it just, I don't know if you guys think it's goofy, but I need to have a picture in my head when I'm trying to get through hard new stuff. And this picture it's just fantastic, I think. So I don't know if you like it, but I like it. So, okay, great. You have a picture, but we're programmers. We can't program a picture. What do you do, right? Well, first we have to think of, our series of operations that we apply. So we have our input layer, and we have our output layer, and then we have our hidden layers. This representation would look like it's some sort of neural net that's based entirely on qubits. And that's kind of, I haven't really found that. I mean, maybe it's in some research labs, but it's more of the combination of the two. So, so it looks more something like this, where you have input, you have your first convolutional layer, you have a pooling layer, and then you have an operation that, because you understand the type of problem and the way the network is modeled, that you could then run using a quantum process. This is actually really important because this is the way that it goes. It does not go where it's all quantum. I've never heard of that. I don't think it's even being shown. Does this make sense? That you take the operation and you plug it into whatever machine learning algorithm?
Yeah, it does.
Cool. Okay. So again, this is a picture. How do you actually do it, right? So all things lead back to Google. So you might remember from the chapter, if you read it, that the operation they talked about was the HHL operation. Even if, you know, the rest of it, what it does is blah, blah, blah. You probably remember HHL because it was in there quite a few times. Well, and it was talking about using Hilbert matrices and Hilbert spaces. This is from Google's TensorFlow Quantum website. I really, really liked this because this helped me to understand, okay, you encode classically into your, you know, n-dimensional space, and then you embed into this Hilbert space, which is super dimensional. That's the way I think of it. And that's why we can get more results out more quickly because of the higher number of dimensions. And then we project it back into the classical space. This sort of workflow is at the highest level what I wish the book would have started with. And maybe this just works for me, but this is the way when I look at the examples that are actually out there, because the book has no sample code and I found a bunch of sample code, which I'll preview to you. This is the way that the sample code goes. So again, I'll pause here. Does this make a little bit of sense?
Yeah, I actually like this because the idea of taking something and increasing the number of dimensions in a way you can tweak and then kind of flatten it again. That's very pleasing to me for some reason. It's almost like you can take it apart and then spin it around and then smush it back together again. And now you're looking at the same thing, but from a different viewpoint, and it makes sense in a different way.
Yay. Okay, good. I'm a good Googler. So again, taking this to a practical, this is from TensorFlow Quantum again. I really kind of like this. So some various operations, prepare the quantum data set, evaluate the model, evaluate the gradients and update the parameters, sample or average. So interesting, you have to read because you have to tune your model. And again, this is different than classical operations because it's a feedback loop. And then you evaluate like what, you know, how effective was my model. Again, I just like this. I thought it was cool. So before we kind of go back into the book a little bit, one of the reasons that I went on this whole journey of this whole book, and I've been trying to learn more about quantum operations, is because of potential applications in the area that I'm working, which is bioinformatic research. And it was interesting because I found a paper, and I'll share this paper that was done in 2020. It was published in 2020. And it's for breast cancer detection using a QCNN, quantum convolutional neural network. And pro tip, if you are like me and you read academic papers, but you're not in school, where do you go first? To the conclusion. So the conclusion is, we have demonstrated the efficacy of quantum convolutional neural networks to detect breast cancer cells. Using the proposed algorithms, we have run the circuit for different parameters and optimized it for the accurate predictions of a breast cancer cell. Remember back in the chapter on images where the sample application was showing noise in the image, and the quantum version, you could detect the noise more easily.
Yeah.
This is an application of it, which an important one. Using the techniques of deep learning and supervised learning in the quantum framework, we've proposed and tested the effectiveness of quantum CNN on the quantum simulator available at IBM. We've considered the application of breast cancer detection to explicate the working of our quantum. We have trained the network of 10 qubits in a way it can learn from the labeling of the given data set and can optimize the circuit parameters to obtain results with minimum errors. And this is the key right here. We have pointed out that the QCNN is not only optimum in terms of the accuracy in comparison with classical CNN, but produces results with better time complexity. I love academics. Why can't they just say faster? So faster, better. And that, go ahead.
Sorry, in looking at the paper, do you know how much faster, like orders of magnitude or?
Yep. Yeah. I mean, it's all in here. So I'll put the paper, the link to it and stuff like that. But the point is, it's, in my opinion, learning about this is hard, but worth it, because there already is some really promising work like this that will change healthcare. Honestly, it'll change healthcare. So that being said, going a little bit back to the book, and then we're going to jump out again. We're going to go in, out, in, out. So he's talking about, things we already talked about. And then they go into solving systems of linear equations because they are trying to demonstrate how the HHL algorithm works kind of academically, which I disagree with the approach because it's too academic. Solving systems of linear equations can result in some applied machine learning algorithms, but it's a path. They're like trying to explain it without doing the math. And I'd rather just go to the machine learning rather than, because solving a system of linear equations is not machine learning, just to be clear. It is pre-machine learning, if you will, because they're trying to give you just a little bit about how this HHL algorithm works. To me, this just really wasn't sticking because it was just kind of a lot of words, and we're not going to really go into it other than it speeds it up, which for me, that's all I really care, right? So HHL, la, 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 uses phase estimation. It's talking about matrices and the eigens, eigen decomposition, eigen basis, eigen vector, eigenvalue, I, right? So again, this just was not doing it for me. So I said, okay, and there's no code. So I'm like, okay, how can I learn this? So I went the other route, which is to look at what the vendors have out here. And the vendors that I've been working with are, I guess I'll start with this one. This is TensorFlow Quantum. And so of course we're developers. So hello, many worlds. Doesn't that sound fun, right? So what is this thing? This is a tutorial that shows a classical neural network can learn to correct qubit calibration errors. So it uses circ that we've seen, and it uses noisy intermediate scale quantum circuits, and it demonstrates how circ interfaces with TensorFlow Quantum. I think it's bait and switch because it's about errors. It's not about worlds, I guess, maybe. So, and it doesn't really have too much with machine learning, but it's the first thing in TensorFlow Quantum. So the question then becomes, why? And the answer is because, as the book said, you need a lot of qubits, and the more qubits you have, the more noise. That's something the book didn't really talk about too much. But as I watch videos and try to learn more about this, all the practitioners say, yes, if we can make these speed ups work, so long as we can address this problem of noise because of the fragility of the different implementations of qubits. So again, there's just so much assumed knowledge here, but it is kind of fun. So, I already ran this. It's not, super exciting. It just says install it. It's nicely written. So, you can just use TensorFlow Quantum, this is new within the last year. So this is again, on the front of kind of what's going on in terms of research and vendors implementing this. So they're just showing, okay, here you've got you've got a circuit. And again, what they use sort of the terse open QSAM, RX, RY. So one of the things that I do like is the way the book took us through the basics helps my ability to be able to read these samples. I don't know if you guys feel that now, if you've gone out to any other samples, but before the book, I would have to look this up and I still might not remember it, but at least I'll have a reference. It's more familiar, like I move forward on my journey. Is it the same for you guys?
Yeah, definitely. I feel like the book gave me a really good familiarity with the different concepts. So yeah, it does make things much easier to read.
Yeah. So then they are working with their simulator. And again, another thing I learned through this journey is the different kinds of simulators, the local simulator and then the cloud-based simulator. And they're two different simulators with two different capabilities. That was a new thing that I hadn't understood before. And really just kind of like you use a local runtime, a local simulator, it has observability in it. And so if you set remember this from previous weeks, the shots to 0, you can actually observe and think how important that is for quantum machine learning, because when you're working through your machine learning algorithm, you're trying to figure out where you would insert a quantum process for optimization. So blah, blah, blah. And then this is interesting, quantum circuits as tensors. So of course, tensors are a primitive object in TensorFlow. I think of them as high-level matrices, and maybe I'm just totally butchering this, but I just think, Google had to have a fancy word for big matrices. I don't know if you guys have a physics background, you can tell me I'm being silly here, but that's how I think of it. All right, and then they basically are just going on to show how this works together. And then they get into the optimization. Okay, now that you've seen the basics, let's use TensorFlow Quantum to construct a hybrid quantum classical neural net. See, this is my point. Every vendor example starts with neural nets because that's what you'd actually optimize. Does that make sense? I thought that was an important thing to bring up in talking about QML rather than the academic focus of the book chapter. So in here, they are showing their different gates, and then they use a concept of a controller, which is, I think this layer right here. And then connect the controller to the circuit. And then apply the operations. And notice they have they would observe to check it. And this is funny. The network architecture is indicated by the plot of model below. Compare the model plot to the architecture diagram to verify correctness. Okay, when Google says that, it means it's hard. It means you might have made a mistake. So is it kind of hopefully making a little bit of sense? These are the layers of the neural network here. So here's the input, and then here's a sequential, and this is another input layer. All right, and then so when you're working with supervised algorithms, which neural nets are supervised for classification, you're going to have to train, and you train with the known good data because that creates your weights and biases for the different values. And that's what this graph is showing. Where is the error? And then you train, and then you validate against known correct data. That's where this graph comes from. So this is kind of like standard TensorFlow code. So you get a little TensorFlow here on the side if you're new to it. So TensorFlow has a higher level library called Keras, which makes it a little bit easier to work with TensorFlow. So again, this is sort of a standard pattern. You have an optimizer, and you can see all these parameters are tricky, lots to learn here. Like, what is the learning rate? How do you know? The point is, you will learn over time, but for machine learning, it's more of an iterative, like you try a value, you look at what the output looks like, you adjust the value. Now, in case you're wondering, there is, Google being the engineers that Google are, there are tools called hyperparameter optimizers. So again, it's machine learning on machine learning, basically. So it spins up a machine learning network to figure out what are the parameter values, which of course they charge you for, because they should, as hours of training time. But anyway, so and then you have the loss, and we're using mean squared error. And then you're compiling it. So that is optimizing it to the lower level TensorFlow code. It's kind of like a C process. And then fit, model.fit is, the fit method is the train method. So train this model in 30 times. That's where the iterations come from here. And then what you're trying to do is see how many times you have to train this, where the errors are at an acceptable rate. And again, the reason for this is you have to train the model, but also if you're going to speed up with a QPU, if this is taking too long, which is a common problem in machine learning, you could at some point or at some layer, and I like Jeremy's explanation of this, I'd call it like explode into QPU space and process faster and then come back. Does that make sense? To speed up the training. That's a common thing. Okay, fine. So that's just Google's first example. Interestingly, Qiskit, which is the IBM Python library for machine learning, and well, it has the machine learning library, it's general quantum library. Their first example is solving linear equations using HHL. So it is the code that the book is hinting at. Ha ha! I found it. So if you want to run the code, it tells you a little bit of math, and then you would have to create a notebook in the IBM environment, and then I'm sure they have the actual sample code on GitHub. But once you get down past the math here and go in Qiskit, there it is. There it is. And just like they did with Shores, remember this, that they just had a method called Shores. They just have a method called linear solver. So it's the idea of wrapping. And I think, Matt, you were talking about this in previous weeks, where it's like, once you get the concepts, it's higher level, you can just use it, right?
Yeah.
Yeah. So, and then this just shows, it also shows the matrix operations. So if you want to do some matrix operations, it shows them to you. So anyway, this shows you the code. And this is literally the example in the book implemented, which I thought was kind of cool. But again, I wasn't super interested in doing the HHL, but if you are, it's right here. So what am I interested in? Well, I want to optimize my neural networks. And so again, just like for the Google examples, Qiskit quickly gets into the hybrid quantum classical neural network, and they use PyTorch, which is yet another machine learning library, and Qiskit. So I love this. I love this diagram. I love simple diagrams. You have the classical part, you have the quantum part, and then you observe the results. That looks like that earlier picture that I showed you with Google, except this one has code. So again, because the book didn't talk about this, and I think that this is going to be the most common use case. Maybe I'm wrong, and maybe they just didn't want to go this far, but I felt like I would be doing a solid disservice if I didn't talk about what I see as the common use case here. And then just like the previous example, they have a more detailed diagram, some math, and then they have the code. So again, I have all these links for, you know, me and you guys and whoever else watching this that wants to get into this, because to me, chapter 13 of the book talks about these concepts, but doesn't really like give you anything as a developer to get your hands on, right? So continuing on our journey here, they have a bunch of libraries in Qiskit, which they even have optimizers for regression, which I thought was interesting because I hadn't really seen that before. So we have all these big fancy words we can say at work and feel smart. We can use a VQR, or I don't know if I'd say use, that might be stretching it, but we were exposed to VQRs, variational quantum regressors, and VQCs, variational quantum classifiers. All joking aside, I do like the fact that there are libraries here because I do want to work at a higher level. And then another area that I found that had a lot of really excellent resources on quantum machine learning is a library from a company called Xanadu. Xanadu makes quantum hardware, and they have a number of libraries. They have another one in their group called Strawberry Fields, which I think is like a Qiskit. It's like a general quantum library, but their PennyLane library is specific for quantum machine learning. And again, they had a really, really nice set of resources. The book, you might remember, has this problem where it shows principal component analysis, which is a pre-processing step where you're trying to understand the data in a space. And I really, really liked the example here, which is a type of a PCA, much better, multi-class margin classifier. It just was written better. And again, it has the code that you can run. And again, the pattern is with libraries. So PennyLane is the library here. So kind of like we're looking at the Qiskit library. So then the last one, I really like the PennyLane convolutional. Here it is. I can barely say all this jargon. Convolutional neural networks. But seriously, I just really thought this was a well-written sample. And because I actually do have customers that want to optimize their neural networks, and we're trying to figure out when to use GPUs and TPUs, this is an actual tool sort of in my toolkit. It's laying on the table. I'm not sure I want to put it in my tool belt yet. I'm not sure, but this tutorial gets me closer to that. And again, similar, it has, I just really like the PennyLane documentation, I have to say. It's kind of beautiful, which is important when you're trying to learn something that's difficult. Just enough, it's not math heavy, and then you just get right into it, and then setting the hyperparameters. And then of course, what are they going to use? MNIST, because that's what we always use. Kind of a little fun aside, people got so sick of MNIST. I feel a little bit validated with this. There's something called fashion MNIST, and it's black and white photos of like clothing. I think it was actually, not that men can't care about fashion, but I think it was actually a set of women data scientists that made it because they were so sick of MNIST. So you could use fashion MNIST if you wanted to, and if you're sick of the handwritten digits. So yeah, and so this is showing the quantum, portion of the neural network. And then kind of to wind this all the way back, kind of fun to look at this. We haven't really looked at Amazon. So I was playing around with Amazon Braket, which is a new service. And you'll see that in their implementation, they have actual QPUs. And it's so interesting how the implementations differ. And D-Wave, of course, was the first people on the block. And they have 5,760 qubits available. That means in total for me as a customer, but I maximum, I think. Notice how the other providers like IonQ and Rigetti have like between 11 and 30. There's a very different number of qubits. And then this is super interesting too. Notice the simulators are problem specific. And the simulators, they have SV1, state vector simulator, TN1, which is new, tensor network simulator, and DM1, which is density matrix simulator. So I'll pause and I'll ask a question. Why do you think that they have 3 different types of simulators?
Well, since it's a simulation, you have to come up with some sort of pseudo quantum way of doing things. And I suppose that they've made it so that it's friendlier for each of these different situations.
Yep. Anybody else? Yes, that's correct. Nope. Okay. That's right. Go ahead.
Yeah, sorry, I started talking and I realized I was on mute. Yeah, you don't have a real quantum computer behind it, so you're not going to get the same performance or ability out of it. So I'm assuming, oh, well, if you want a simulator that's going to be as accurate as possible, we're going to purpose build one for you for your type of problem.
Yes, yes, and that's actually the key point. You both hit on it, but I just really wanted to drive it home. That's super important because it's not a one size fits all. That's super, super important. And it's not a classical problems or machine learning problems. It's not that simple. It's within machine learning. Are you doing a neural network or are you doing PCA or, what are you doing? So this is really important in terms of understanding how to work with quantum in general, but machine learning very, very specifically, that you have to have the right kind of understanding of your problem space. And the simulator differences allow you to do that. Go ahead.
I don't remember if we've talked about this earlier, but does that also kind of flow over into the actual quantum machines where some of them are better at certain types of operations than others?
Completely. And even to the point, I don't know if I can't remember if I showed you this last week at Shores or not, but in some of the samples, I think it could be the Amazon here. I'll show you in a minute. One of the operations that you do when you use the simulator is you then, before you try to run it on the actual QPUs, you do a check to see what operations are supported. Because again, it reminds me of just the early days of any type of technology where there's not standardization, right? And you have to validate. But for the kids who haven't been around as much as us experienced people, this is a new concept because they're just used to just programming, in their language, and they don't have to worry about the hardware. I think for many developers, but you really do here. It really varies. So well, the way that it works here is you make a notebook, Jupyter notebook, and then you have a bunch of samples. And then once you run tasks, you can look at the tasks. So I've run some tasks here. So it's like the IBM implementation. So just to show you, so they have the Braket examples. It's interesting that Amazon integrates with PennyLane. So they have some other things as well, but so, and they even use like all of the fun graphics and everything from PennyLane. So they really want to, for PennyLane users, they want them to be really, really comfortable on Amazon Braket. And this is just getting started on, I guess I could actually run this. And you can see it's a Conda package. Braket is a Python library for this. And then this is not doing really machine learning. This is like pre-machine learning, basically. You're setting up. But I like the documentation in here. And here we're just just kind of doing basic quantum operations. We're not doing anything machine learning yet. So, but it is nice that it's, the syntax we should be familiar, RX, RY, C naught. And then they expressed the polygate. I think it was different in the QC engine, but we've at least heard of the concept, right? So, and then you're just kind of, they're just like kind of taking you through the circuit. And then, you're just getting the information out from the circuit. And then, we may have complained about the circle diagrams, but this is what you get in here. So I think the area of visualization of execution is a really ripe area. Kind of like, that's why I included TensorBoard in this discussion, because I think Google has done a lot with neural networks around TensorFlow. And it'll be really interesting to see what they do around visualization of quantum operations and circuits. And so then you're just going along, and here you're actually training. So you're using a gradient descent optimizer. So you're doing real simple machine learning. And then I guess I should run everything. So you got the circuit, and then you're going to evaluate the gradient, and then you're going to train it, setting the parameter of the step size, like how, what's the space. And then again, our familiar curve, right? That we saw in the earlier example, because what we're trying to do here is we're trying to see the cost optimization. So it's a lot of stuff, but it is a similar path across these different vendors. And then you can run it on the managed simulator. And so they say use SV1. And so we've been running on the local simulator, which is running on basically the EC2 instance. Does that make sense? So earlier we're okay. So then we're running along here, and here we're setting the device to our simulator, which is kind of cool. And then we need to choose a place to store, because it's kind of a data lake kind of thing, where you get your data from S3 and you put your data back out into S3 and you do the computation on the cluster. And then this is how you access this Braket AWS Qubit. And again, I really like the fact that they are, sort of saying, okay, we're just doing something basic here. This follow-up tutorial shows you how to use the remote device to run multiple circuits in parallel, while this QAOA tutorial takes a deeper dive into graph optimization. This is another problem area. If you guys have heard of the traveling salesman problem, it's a common problem in computation. And it's something that obviously a lot of businesses have to deal with. It's most effective routing, and quantum speedups can positively impact that as well. So that's another research area. So let's execute our circuit on SV1 as well as calculating the gradient. And then it'll come back here and ooh, 99%. Okay, yes, that's good, right? But it's not as exciting. So it's some of the visualization stuff. So you'll see the very next thing they have is how to parallelize that using quantum. And then they go into that graph problem, and I'll just briefly quickly show you what that looks like, which to me is really interesting. I actually have a customer who has that right now. They're doing routing for some service provider, and we really might actually try to use this, because they are trying to do classical ways to optimize the routing problem. So again, to me, it's important to understand, like, okay, you can optimize for classical and machine learning. What are the problems you want to work on, right? Unless you're a researcher and you can figure out what the problems are. I'm a practitioner. I want to know what the problems are and then just try and see if this will make it faster, right? It seems much more practical to me. So anyway, one of the things that I would tell you is when you get into some of these problem spaces, like this is on chemistry, which is another area, the visualization of biochemical structures. They do, when they get down to the bottom of it, they have great artists here. They do tell you, is it this one? I can't remember. No, I guess not this one. When you get into the quantum chemistry one, which is here, this one, they do tell you, don't uncomment this code unless you want to pay and wait 15 minutes to 30 minutes. And if you run this on the actual quantum device, you could be paying a lot of money. And so I want to be respectful of people's resources, and do say that when you are running on a cloud vendor, even on the simulator, they're charging you. not a lot on the simulator, but if you run on the actual QPUs, you better know what you're doing before you run those. I think they actually have limits set. And so if you're going to hit, they'll do an evaluation of what you're trying to run. And if you're going to, it'll be kind of like, are you sure? Before you press the OK button. So in any case, what I have done is I have put all this information in here. So this is basically everything that I talked about today in chapter 13 as augmenting it. And then I summarize the chapter here, because the chapter really is covering linear equations, PCA, and SVM, which are academically interesting, but I don't really see them used as QML anywhere from a practical point. So, if you want to learn academically, great, but if you want to do something that has potential practical application, I would say neural networks is kind of where the action is. The thing that seems to me to be the most necessary, like for my own further learning, is to understand the requirements around the matrices, because the book did go into that quite a lot on the type of matrix, the fact that it has to be sparse, that it has to be decomposable via the eigen whatever. So it has to have certain characteristics to be optimizable. That seems to me to be an area to do more. So in any case, that was what I took out of the chapter. I do not know if that's what you guys all took. I would be interested to hear anything you would have to say about my little journey as we talk about this chapter.
Yeah,
I'm not an ML guy, so one of this was new to me, so I'll let other people talk. I did have a couple of questions as we're just wrapping up the whole book in general, but I'll defer those till we're done with this.
Yeah, the book chapter was not very helpful to me, and that this is much more so because looking at the practical things that are available and explanations and tutorials gives me somewhere else to go and look and start exploring that.
Nuri, you are oddly quiet. Are you just thinking, or are you
Yeah,
sleeping?
I think my sense today is I did not grow my understanding of quantum, but I got a bunch of leads that seemed like cool if I wanted to dig deeper.
Yeah, well, the TLDR is you have to learn neural networks first, honestly. And that's a pretty big hurdle. But it's not, I don't think, worth the effort to try to do QML unless you're going to do CQML or QCML, whatever.
The other random thought of the day is, you remember that era with everything was iPod, iPad, iStorage, iMac, iBurger King. So now it seems like everything is Q. Q bits, Q algorithm, QML, Q haircuts, whatever.
Yeah, in the computing field, I'm comfortable with that. I'll put it that way. So Matt, since we're winding up here, do you have any questions or any comments or anything you want to add?
Well, as you were showing some of those other quantum computers and stuff, and you have in the cloud background, why does D-Wave seem to have such a large lead over some of these other extremely well-funded companies? And are there 5,000 qubits available, legitimately the same qubits that other people only have 20 or 30 of? Are we losing something by D-Wave having
that is an excellent question. So D-Wave did come first. But their implementation of qubits has been hotly contested from the beginning. They use something called quantum annealing, and it is a different way of building qubits and interacting with qubits than some of these other vendors. And so some people, have flat out said those aren't qubits. So it's been really, really interesting. Now I feel like I have enough knowledge, I could actually try to answer that question. And I don't know if your sharp eyes caught it, but in the Amazon samples, because they have D-Wave and not D-Wave, they have some samples around annealing, which interestingly, the book did not cover. So I am curious, Gal. So that's a great question. It's a place for exploration. Like, what are qubits that are annealed, and what can you do with that? And
And it seems like every month or every few weeks, actually, you're seeing some article that someone's created a new way to, harness a quantum bit. And I'm wondering, okay, there's all these different ways. Some are obviously probably more cost intensive than others, but I would assume there's trade-offs as well. So what if D-Wave is, let's say, faking their way to the front? Is the end result the same? Or are we going to find out, well, they've got 5,000, but really there's so much noise.
Right.
They're having to really scale that back, or are they racing to the pack and saying, well, yeah, we're using a lower, type engine, but the end result is still able to do QPU type, projects on.
Well, again, what I would use for evaluative purposes is Shor's algorithm, because that's the quintessential, classical versus mixed algorithm as a starting point. And then I want to learn how to use MNIST on a QCNN as my starting point, because I'm more interested in that than Shor's algorithm.
Yeah.
So, places for learning.
Yeah, and the other thing I was curious about, you mentioned paying for time on a CPU. So when I think of paying for time, like, on cloud, you got EC2 and you got other stuff, I am literally paying, they're going to spin up some resources for me. I can use them. And when I'm done using them, they'll probably spin them down or hand them off to someone else. But there's a finite number of QPUs out there. So I'm wondering, and I'm gathering you don't just automatically spin them up and spin them down and not be used. I'm sure there's some cost involved in keeping them in a usable state, but I'm just wondering what the queues for those types of work are. If I were to pay for some time and submit a project, is it waiting for hours and hours for my spot in the queue because there's only a small number of these? Mm-hmm. Or are they lying around just waiting for people to pay for them? And in the meantime, they're just sitting there doing nothing, collecting dust because no one's.
Well, one thing I noticed when Lynn was showing the Amazon is one of them was listed as having like a 16-hour wait until it's available. Okay. And the counter was actually counting down, and then it got bigger, assuming someone submitted jobs to it, and so it got bigger and it's still counting down.
I noticed that also with the IBM simulation environment, you could actually run it on real QPUs with like 1 bit, 2 bit, 3 bits. So measly number of qubits available to you as hardware, but they had queues, and it was kind of cool. You look at the dashboard and it's like, oh, the Melbourne one has only one in front of you. Quick, type it in.
Yeah. It's
but
like,
I assume that's how they use spare capacity, is for teaching and stuff like that. But it's a good question. Who's bankrolling the energy expenditure and making it available? So if a rich cat with some deep pockets came along and wanted to run a real job, that they could get it right away.
Well, the number one investor in D-Wave was Jeff Bezos. So there you go. So everything runs on a queue. In my playing around with Braket, sometimes I had to wait longer. Sometimes longer could be an hour. Sometimes it ran right away. So my feeling is that for the public on cloud, it's relatively small. But that there are some fintech customers that are using QPUs in production to optimize, and companies like Uber, for example. So that routing algorithm, they're using it for routing their drivers. So it's not, super way out there. Nobody's using it. It's just a small number of people. So that being said, I'm going to stop the recording and thank everybody for their journey.